like to thank a couple of people who make this talk possible, starting with Carly, Mike, and Alyssa for once again this year organizing a great conference on women's hockey analytics. I would also like to thank Snorri, Nolan, Tyrell, and Katya for providing great feedback, whether it's on the statistical modeling process or the data visualizations that you'll see in today's presentation. So when talking about the DEVe models, the four things that we'll talk about today are going to be the motivation for this study, the statistical methodology to develop this framework, the insights, which includes women's hockey aging curves, retirement rates, as well as league/player case studies, and we'll wrap everything up with key takeaways at the end of the presentation. So in terms of motivation for this study, it all started a couple of weeks ago when a player reached out to me on Twitter asking me a very simple question: where should I play next year? And so at the time, I didn't quite have an answer for her or a statistically robust answer. So what I did is that I looked at her historical stats and projected them into many different leagues around the world. And knowing the player as well a bit, I advised her to stay in the league in which she was currently. And then if she's looking to move again next year, I advise her to maybe think about doing that after the year that's about to come. But this conversation that I had with this player was actually very interesting because it got me thinking about aging curves in a way that I hadn't necessarily thought about before. It got me thinking about the impact that different leagues and different development trajectories might have on the offensive production of players through time. And so for the methodology regarding this project, the starting point for the aging curve project, that is DEVe, was the women's hockey metric, which we actually talked about last year at this conference, WHKYHAC 2021, with Holly Morrison and John Bouchard. If you're not familiar with this metric, it's basically a way of quantifying and standardizing offensive production across many different leagues around the world. And so if you want to learn more about how this metric is actually built, I invite you to go to the YouTube channel of Women's Hockey Act to watch our presentation from last year. But keeping in mind that this was the starting point of our project, I did some research online a couple of weeks ago when I got that idea and came across this project from Connor Jung on NHL prospects and NHL draftees regarding the projection of points in time. And what was very interesting about this particular Apple project from Connor was that it was not only projecting points in time, but it was also letting the model recognize that there could be different trajectories and different paths for players to get from the initial league to the target league, which is the NHL. And so when thinking about my DEVe framework, I wanted to build a set of models that would project production in time, but also take into account and predict the league in which players will play down the road to factor that into the point projection, whether we're talking about high school players, college players, or professional players. So the DEVe models are separated into three submodels, M1, M2, and just to keep it simple, M3. And each submodel answers a specific question. So model M1 answers a binary classification question, which is, will a player retire or not after a given season? The M2 model is a continuation of the M1 model and looks at the scenario where a player doesn't retire. And if the player doesn't retire, the M2 model answers the following question: in which league will this player play next year? And once we have this information, we can plug it into the M3 model to determine how many points this player will be able to put up in the league that was predicted as part of Model M2 in the coming year. And so Model M1, as I said, is a binary classification problem looking at the retirement and or not of different players. And so the simplest way in stats to solve binary classification problems, or one of the simplest ways, I should say, is to use logistic regression. And just to keep it simple for Model M1, that's exactly what we did. The target variable here is equal to 1 if the player retires at the end of the year, and is equal to 0 if the player doesn't retire. This retirement classification is based on a number of predictors, covariates, independent variables, which include the age of a player, the offensive production of the player in the form of N women's hockey, and the position in order to separate forward from defenders. Then we have Model M2, and as I was saying, it is a continuation of Model M1 in the sense that it looks at the scenario where the player doesn't retire. And in this particular Model M2, we want to predict in which league a player that won't retire will play next year. So this is a bit more complex of a classification problem than the previous one, since there are many different leagues in which a player could play next year. So to solve this multi-class classification problem, I used a random forest classifier with a one versus rest approach, which is the default in sklearn in Python. And so, as I was saying, the target variable here is one of the 40 plus leagues as included in the N Women's Hockey project from last year from around the world. And the algorithm will actually spit out the league that is most likely to host the player in question next year. We calculate this variable, or we determine this variable with the following predictors, which are pretty similar to Model M1, including age, offensive production in the form of N women's hockey, position to separate forwards from defenders, and we also add the league in the current year to make our prediction for next year. Some interesting observations regarding models M1 and M2 include the following. One question that some of you might rightfully ask is why build two separate models for M1 and M2? Why not include the retirement as an extra league or an extra category in the multi-class classification problem of model M2? And to be honest, that was my initial thought. But what ended up happening as I was doing validation tests with model M2 and the random forest classifier, the retirements for different players were not being correctly predicted. And it was skewing the results solely looking at this category as opposed to what we were expected to get. And so for that reason, I decided to take a step back and build a simpler model for the retirements, looking simply at a logistic regression with a couple of variables to better model and better capture the linear relationship that exists between retirements and our predictors. The other thing is that there is an underlying data assumption that exists in our models that leagues in the future won't change. And that's an assumption that we have to make when building models like this one, just because we can't predict how the landscape of women's hockey is going to evolve through time. But obviously this data assumption is wrong because, as you may know, the landscape of women's hockey evolves very quickly. And so down the road, and maybe next year even, when and if new leagues appear, it would be key for us to rerun models M1 and M2 in order to make sure that the data and the results that we're predicting are as relevant as they can be given what's actually happening in women's hockey. So moving on to model M3. So as I said, model M3 is the points projection aspect of this project of this aging curve project, and it answers the following questions. How many points will the player put up in the league that we predicted as part of Model M2 next season? So this is a continuous target variable that we have in the form of N women's hockey for next season. And to solve this problem, I decided to use a random forest regressor. We could have used a simpler model like a multiple linear regression, but there is some non-linear and more complex relationships that may exist between our target variable and our predictors, which we'll talk about in a second, that the random forest regressor allows us to capture. And that's why when comparing the random forest regressor and the linear regression with multiple variables, the random forest regressor was significantly outperforming our simpler model. So the covariates, or the independent variables, the predictors in this case, are the age, the N women's hockey, and the position, like the two first models. But in this case, we look at the league, which was projected from model M2 in order to make our prediction regarding the future N women's hockey of the player next year. So moving on to the insights that can be gathered from our project. First, let's take a look at a couple of aging curves based on N women's hockey. So in this bar chart here, I have the evolution and distribution of N women's hockey with age. So on the y-axis here, we have the average N women's hockey. And on the x-axis here, we have the age of different players going from 15 to 41 years old. And so we note a bell-shaped curve here, peaking around 26 or 27 years old. And so the main conclusion from this aging curve is that women's hockey skaters peak around 26, 27 years old, separating the players into different positions. So looking at forwards versus defenders, we observe two additional bell-shaped curves, which is interesting. But looking at the differences between these bell-shaped curves, we note that forwards peak around 26, 27 and are able to sustain some production into their 30s, while defenders peak a bit earlier, around 26, but don't sustain production for as long as forwards can. So you can see around 32 years old here, the bar chart is significantly decreasing in distribution as well. Moving on to retirement rates, we can visualize the rate of retirement versus age with this graph. So on the y-axis here, we have the rate of retirement based on the total number of retirements divided by the total number of players at a given age predicted by the model. And what's interesting is that obviously there is not going to be many retirements before the age of 22, 23, where this is where usually college careers end. But when we start reaching the mark of 28 years old, over 33%, so over a third of players are going to retire each year. At 30 years old, this number of retirement rate becomes over 40% each year. And at 34 years old, we're talking about over half of the players that are going to retire each year, which is an interesting concept of seeing this curve evolve. Again, when separating the forwards from the defenders, we note similar insights to that we were talking about with the aging curve, in the sense that on average, defenders that are represented by the pale blue curve here retire sooner than forwards. And so basically, not only do defenders not sustain production into their 30s, but they are also more likely to retire than forwards at any given age, except here where Jenny Hirakoski and her predictive modeling process kind of skews the results in favor of defenders. In terms of the individual and the league insights that we could get from the DEVe models, we could take a look at the individual player aging curves. So what I did here is that I ran my models for the next 4 years and tried to project the women's hockey based on models M1, M2, and M3 of different players through time until I think 2026, 2027, if I'm not mistaken. And then I identified the 4 players who had the most offensive upside based on these models. And I'll explain to you what I mean by offensive upside in a couple of seconds. So these players are Alina Mueller, Josephine Bouvin, Michaela Grant-Mentis, and Petra Nieminen. So going case by case, what the model predicts for Alina Mueller is that when she finishes her NCAA career, she will be moving on to the PWHPA. For Josephine Bouvin, who's actually committed to the University of Minnesota for next season, the model doesn't quite predict her switch to the NCAA. And that is interesting because there aren't many Swedish players that play at her level, first of all, for her age, but there aren't many Swedish players that are going to make that switch either from the SDHL to the NCAA. And so it is kind of normal for the model to not pick up on this transfer, which is going to happen next year. Michaela Grant-Mentis is expected by the model to continue in the PHF, while Petra Nieminen is also expected to continue in the SDHL in Sweden with her team in Luleå. So the interesting thing when I showed this graph to a coach in the SDHL a couple of days ago was that he told me that I was talking to him about the players with the most offensive upside, but that most players in this graph had a downward trajectory in terms of expected women's hockey. And that was a very good point he made, because when thinking about women's hockey, this point that you see that is the projection for the following years is only representing the average of the projected model M3. And so given that development is not something that is clear-cut and that it is influenced by a variety of circumstances, one important thing when thinking about player development is not looking at specific precise numbers, but rather looking at ranges of possibilities in which a player could fall, in which a player could evolve in the next few years. So taking the example of Alina Mueller here, you can see these little points that are grayed out in the graph that represent a 90% confidence interval calculated as part of model M3. So that's the model calculating the future women's hockey. And so what I told the coach to answer his very good question was that even though this is the average expectation, there is a 90% probability that the production of Alina Mueller next year falls in this range. Same thing for in 2 years, there is a 90% probability that the production of Alina Mueller falls within this range over here. And so when thinking about development, it's very important to think about it as a range rather than as a specific number, just to be more precise with the different possibilities of development. So what are the key takeaways from my presentation today? First, we saw that women's hockey players peak around 26 or 27 years old, and forwards, as we were saying, stay productive longer than defenders. Forwards are also likely to play longer than defenders, which is kind of in line with our aging curve results. But when looking at the overall players in women's hockey, at 28 years old, over 33% of players are likely to retire. Finally, if there is one thing I would like you to remember from this presentation, is that when analyzing development trajectories and looking at aging curves, it's very important to consider uncertainty and consider the ranges of possibilities that may exist for development. Player development, like scouting, isn't a perfect science. And so having that range rather than that specific number allows us to be more precise, but allows us to have a better assessment of the expectations of what's about to come for different players. Thank you very much for taking time to listen to my presentation. I now open the floor to any questions you may have.